Okay, we now consider another twist with regard to the aldol condensation reaction. And that is, upon heating, aldol products can undergo a base-catalyzed dehydration reaction. Okay, so what do we mean by that? So the aldol product is the beta-hydroxyaldehyde in this case, and when you heat it up, the OH at the beta carbon goes away, the H, one of the H's at the alpha carbon goes away, and we form a double bond between the alpha and beta carbons. And this product is called an alpha-beta unsaturated aldehyde, or ketone if you were starting with a ketone. And this reaction is called a dehydration because a molecule of water is formally lost. You don't actually kick off H2O, you remove H first and OH minus second, as we'll see when we look at the mechanism, but we're still formally losing the elements of water. The driving force behind dehydration is that, as you can see, the product is conjugated. You have a CC double bond separated from a CO double bond by a single bond. And as we have already discussed in previous videos, conjugated molecules are unusually stable relative to non-conjugated molecules. So if you can get conjugation, you're going to. Okay, so the mechanism of dehydration, the first step is a proton transfer step, where we use the OH minus that's present in the reaction flask to remove the alpha hydrogen, the hydrogen from attached to the alpha carbon to the carbonyl, to form an enolate. This should not come as a great surprise to you. We have seen alpha hydrogens being removed to form enolates throughout this unit. But then the second step is that the electrons that are left behind on that carbon go to form a carbon-carbon pi bond, and at the same time kick out OH minus as a leaving group to give the product. So you may say, I don't like OH minus as a leaving group. Well, the reaction is taking place under basic conditions. And OH minus is a good enough leaving group under these basic conditions, and it's actually a weaker base than the enolate that we generate in step 1. So step 2 is fundamentally, I know it's loss of a leaving group, but if you think about this step in terms of pKa's, you are generating the weaker base. Okay, another note about this mechanism, especially about step 1, you may be asking the question, have I not removed the most acidic hydrogen? And the answer is no, I have not removed the most acidic hydrogen. The most acidic hydrogen in the beta-hydroxyaldehyde is the OH hydrogen. That's got a pKa of 16. The alpha hydrogen that gets removed has a pKa of 19. We are going after the second most acidic hydrogen. If we went after the most acidic hydrogen, which undoubtedly happens, that takes us down the retro-aldol path back to starting materials. In order to undergo dehydration, you have to remove this second most acidic hydrogen. The fact that you are removing a hydrogen that's not the most acidic explains the need for heat in this reaction. Making the conjugated product is the thermodynamic driving force, but removing this hydrogen in step 1 has a reasonably large activation barrier, and the heat helps us overcome that activation barrier. Once you generate the enolate, it's going to want to kick off OH minus, and step 2 of the dehydration actually drives step 1, as we have seen for many other reactions. Okay, so our complete reaction of aldol plus dehydration is depicted here. 2 molecules of acetaldehyde treated with NaOH in the presence of heat gives the 4-carbon alpha-beta unsaturated aldehyde. So notice that after dehydration takes place, you now actually have a double bond where there was no bond previously. okay, between carbons 2 and 3 of the 4-carbon chain. So the overall process has not only created one carbon-carbon bond, it has created 2 carbon-carbon bonds. And that's a good thing from the point of view of a chemist. When we generate alkenes, we have to consider the concept of alkene stereochemistry. So what I have drawn up here in the first example is a transalkene. But you can think that this reaction, hypothetically at least, could give the cisalkene as well. What you have to know is that dehydration will favor the formation of transalkenes because they are less sterically hindered than cisalkenes. In the cis case, you can see how that methyl group is getting close to the carbonyl group, and in the trans, everything can get out of each other's way. So therefore, the transalkene is going to be the major product, and the cisalkene is going to be the minor product, and I am okay if you just draw the transalkene as a product of this reaction. So another point that I want to bring up is that if dehydration of an aldol leads to extended conjugation, okay, that means more than just 2 double bonds in conjugation, dehydration will take place even at room temperature. So if we consider acetophenone as our starting material, it's a ketone and it's got an aromatic ring, the initial aldol product cannot be isolated, the beta hydroxy ketone. This is spontaneously going to undergo dehydration to give the alpha beta unsaturated, because look at what's going on in this product. The new double bond that we have formed is conjugated to both the aromatic ring and the carbonyl, and in fact the other aromatic ring is within the same pi system. The 3 carbon atoms on the chain linking the 2 aromatic rings are all sp2 hybridized and can all contribute to the conjugated pi system. Okay, so as a result, this is a very, very, very favorable reaction. So that may lead you to think, wait, didn't you just draw the aldol condensation of a ketone? And didn't we say in the previous lesson that the aldol condensation of a ketone favors the starting materials? Well, this is where dehydration helps you out, because under conditions that promote dehydration, so heating if there's no extended conjugation or the formation of extended conjugation, that will drive even aldol reactions of ketones towards product. Okay, and here is some data to show you. So cyclohexanone, an ordinary garden variety ketone, if you do the reaction cold so as not to get dehydration, as we've already discussed in a previous lesson, you're only going to get 20% of the beta hydroxy ketone product. Most of it will stay as starting materials. But if you heat the reaction up so that dehydration can take place, 90% of it goes to product. Why? Because initially the equilibrium is going to favor the ketone starting material when there's an equilibrium between beta hydroxy ketone and the ketone starting material. But when the equilibrium is between conjugated product and unconjugated starting material, that equilibrium is going to favor the conjugated product. Okay, so the product is so much more stable with conjugation that once you get to that product, the dehydration product, it is not going to go backwards. Okay, the dehydration step can go backwards. We will discuss how it can go backwards in a subsequent lesson, but at least for the context of this lesson right now, once it happens, because you're generating conjugation, it's not going to want to go backwards. So that allows you to get to aldol products even with a ketone. Okay, so the aldol plus dehydration product actually looks nothing like the starting materials anymore. So I just want to close this lesson out by going through an algorithm of how to draw the product. Because remember, we are going to have two new carbon-carbon bonds. We're going to have a new carbon-carbon double bond. So the way I think you should look at this is, if we're doing a dimerization reaction, first of all, identify alpha hydrogens that can get removed. So in this case, they're indicated in red here. So then we want to draw another molecule of the ketone. Remember, we're bringing two molecules together in the aldol condensation, such that the oxygen of the ketone is in close proximity to two of the alpha hydrogens of the other molecule of ketone. Now you can simply remove the H2O and link together the two carbons with a carbon-carbon double bond. And that's going to get you to the alpha-beta unsaturated carbonyl product. And finally, when you are considering stereochemistry of cis versus trans, you're going to want to draw the transalkene, or the one that is least sterically hindered. You will have plenty of opportunity to practice doing these in the course of working practice problems.